Hi students, so the topic that we will look into today is on further sequence and series. As you are aware, in semester 2 we did the sequence and series topic where you learn about arithmetic and geometric progression. So now we will look into um, power series and Maclaurin expansion for this chapter. So there are three learning outcomes for this chapter. The first one focuses on how to recognize a power series. So I will highlight the characteristic of a power series, and the second learning outcome will further look into how do you actually do a Maclaurin expansion for a given function and up to specific required terms. So example, obtain the Maclaurin expansion for the first 7 terms or the first 5 terms. So you are required to expand up to the specified number of terms required. And the third learning outcome will actually require you to determine another Maclaurin series, but this time it will be for composite functions, meaning two functions combined together. So now we will look into the first learning outcome, and we have seen that previously in geometric series, an example is 1 plus x squared and so on. Okay, this series converges when x is between -1 and 1 and it diverges otherwise. A series of the form of similar to geometry, but it has a coefficient of a0 and a1, a2, a3 in front of the x squared and x cubed. If you observe the difference between the second function here, the first function, and this is referred to a power series where the coefficients a0, a1, a2 up to whatever number of ar are actually constants. Okay, so this is known as a power series. Okay, for example, if we need to express e to the power of x as a power series, so now we will have a look at how do we actually express this power series. So the first initial step would be equate fx as ex. Okay, because ex is the function that you want to express as power series, and power series is generally written in terms of a0, a1x, a2x, a3x, as is shown in the previous slide. Okay, so the next step would be you need to identify a0, a1, a2, a3 in order to write the power series for e to the power of x. So we're going to see how are we going to identify all this. So the first step would be you substitute x as 0 into fx, so it will arrive to e to the power of 0, which is 1. So therefore a0 is 1. Okay, the next step will be to show you how to identify a1, a2, a3 and so on. So when we differentiate f prime x, we'll actually get e power x. Okay, and then when we differentiate the function which is on the right that contains a0, a1, a2 and a3, you will obtain this function. So now when you differentiate a0, because a0 is a constant, so and we already found the value of it is 1. Okay, and when we differentiate 1, it will definitely give you a 0. Okay, that's why you see a0 is missing from here because it's a 0. When you differentiate a1x, it will arrive to a1. Okay, differentiating a2x squared will give you 2 from x squared is brought in front, so 2a2x. When you differentiate a3 x cubed, a3 is a constant, so you maintain the a3 there. Your focus is just differentiating the x, so it becomes 3x squared. So you'll get 3a3 x squared and so on. If you have a3 x4, a5 x5, when you differentiate, it will be written in such a way. Okay, so next now we can actually identify f prime 0, our next step 2, right? So we differentiate f prime x, when we differentiate fx, which is ex, we will actually get ex again, and then f prime 0, substituting x as 0 into f prime x is substituting x as 0 into e power x will actually give you 1. So therefore your a1 is 1. Your next step would be differentiating fx, this differentiating fx twice, or simply differentiating f prime x to get f double prime x. For this function, you will still get e power x, and when you substitute a 0, you will actually get 1. Okay, the function over here is simply writing out the equivalent differentiation. So when we differentiate f prime here, differentiating a1 because it's a constant, it will be gone, and you will be left with 2a2, because x, when you differentiate x alone, it becomes a1. Okay, differentiating 3a3x squared will actually give you, leave the 3 alone, is a constant, a3 is a constant. Okay, differentiating x squared gives you 2x, so we add 2x here to this term. Right, we'll arrive to this. And next, when we differentiate x cubed, it will be 3x squared. Right, as you can see, 3x squared being added to this term above here to get the term below here. Right, and so on for ax power 5 and so on. And then our next step will be substituting x as 0. It will simply give you 1 as well. And so in this case, comparatively, 2a2, when we compare, 2a2 actually equals to 1. So a2 is actually half. Okay. Next, when we have our next step will be to differentiate e power x in the third level. All right. So when we differentiate it again, we will still get e power x, and when we differentiate f double prime x, right? So 2a2 will be gone because a2 is already a constant, and then we will have 3. We will have 3 multiplied by 2a3 because the x will be gone. So when we differentiate, just focus on differentiating the x. So this becomes 2x, okay, and this becomes 3x, okay, and so on if you have more terms. And then next step, again, you substitute x as 0 into f triple prime, and you will actually get 1 again. So therefore, you can solve your a3. All right, so a3 comparatively, it should be 6 times a3 equals to 1. So therefore, you will get 1 over 6. And then next, this process, when you repeat it, it will keep on repeating indefinitely. And because I didn't specify here what are the number of terms required, so in our next learning outcome, you'll actually see what are the number of terms required. So you can stop at where you're required to answer any questions. Okay? So this is the basics of our series. So now we move on. You see, you can actually write your power series in these terms. This is the working we done in the previous slide. We substituted the A0, A1, A2, A3, A4, A5, and so on. So in other words, you can write it like that, because if you actually observe the denominators, they are actually factorials. 1 factorial over 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial. Okay, so it's actually a pattern. This is how you actually write a power series for e power x. Okay? And it's valid for all x values here. Now, in other terms, this particular power series is known as the Maclaurin expansion for e power x. Let us consider to write general functions. So example, if fx is a0, a1, okay, so this is like a write in a general form. Okay, so your first step here will be letting x as 0, I repeat, and you will get your a0. Next step is we differentiated, remember, and we differentiate the fx, and also we differentiate the terms that contains the a0, a1, a2, and so on, and then we can obtain our a1. Next step will be we differentiate f double prime, we differentiate the terms in the terms on the fx, and also the terms that contains the a1, a2, and so on, and we obtain this. Next, we will substitute x as 0, we'll get 2a2, so therefore a2 will be whatever the value of f double, whatever function f double prime x, the value you get when you substitute x as 0 over 2. Next, the third step will be differentiate it the third time again. We repeat the process. Okay, and next we will get f triple prime. We substitute with a 0, right? Obtain the value of a3. Okay. And this process can be repeated indefinitely. Yeah. Next, in conclusion, we can actually write our Maclaurin expansion in such a way. As you can see, is f0, f prime 0, f double prime 0, f triple prime 0 is a pattern. 0 factorial, 1 factorial, 2 factorial, 3 factorial. So this is like a fixed formula. The previous slide I showed you how actually the write-up of a power series or a Maclaurin expansion is actually derived. Okay, so we can also write this in a summation form, where fx simply means summation of n equals to 0, because here n is 0, yeah, remember? Okay, and 0 to infinity, because it can be written indefinitely, right? F power n, as you can see, the power here is 0, 1, 2, 3, and so on when you differentiate it. So it's power n over n factorial. As you can see, if it's 0, the first one, 0 factorial. If it's 1, differentiated once is 1 factorial, differentiated twice is 2 factorial. So there's a pattern here, fn and n factorial. Okay, and obviously we substitute 0 each time because this is f0, f prime 0, f double prime 0, and so on. And x, of course, to the power of n, because as you can see here x is power of 0. So if n 0, n factorial is also, n is also 0, so x is also 0. Same goes here. F prime is 1, right? F prime 1, so n is 1, 1 factorial, x power 1. Okay, so that's how we can write. It's written as sum because we add each of the term. So this is how you can actually express it more concisely. So in this case, when you further your studies in the future, you might need this limits and approaching infinity. Next, let us explore power series of a trigonometric function. Yeah, so fx equals to sine x. So for example, if you're required to find power series for this function, so yeah, this is the formula to get the power series. So obviously, based on this, you need to get f0, f prime 0, f double prime 0, f triple prime, and so on. So that would be your easiest, the first step that you should write it systematically. Yeah, fx and then f0. Remember, we did that the similar process for e power x. And then f prime, first derivative, and then substitute x as 0. And then second derivative, substitute x as 0. Third derivative, substitute x as 0 again. Okay. And then fourth derivative, substitute x as 0. If you want to move on to the fifth one, and then you want to do more, it's fine, right? Just to see the pattern. Okay, so this process will be repetitive, yeah. Okay, so you can substitute your f0 and 0 factorial into the function above. That's the formula, right? So you can actually get, you see, if you substitute f0 was a 0, so you will not have all terms here because it's sine and cos, because f0 is a 0, f double prime is a 0, f power 4 is also a 0, f derivative 6 times is also a 0. So you will not have all the terms here. The terms that are 0, we normally don't write it out. Okay, so just focus on the terms that has a value. So in this case, f prime is 1, right? Yeah, so it will be 1 over 1 factorial times x. You will actually get x, right? Next, you will not have any value for f double prime because it's a 0. So you'll move on straight to f triple prime. So you'll get a negative 1. So it will be negative 1 over 3 factorial x cubed, right? So that's negative 1 over 3 x factorial x cubed. Okay. Next, you will have no any value for f4, but you can have value for f5. Right? f5 will be simply 1 over, it will be negative 1, right? Yeah. It will be negative 1 over 7 factorial. times, sorry, with 1 over 5 factorial times x5 for f5. And for x7, it will simply will be negative 1 over 7 factorial x power n, which is 7. And simply because this is a power series and there is a continuity, is indefinite. So when you write out your answers, you need to write plus dot dot dot. That means there is a continuity simply because it's a series. Okay. Next, we will move on to the second learning outcome. We want to determine the Maclaurin series expansion for a given function to a specified number of terms. So before this, we said the process was indefinite. Now we want to specify the number of terms, okay, that you need to calculate. So for this question, use the Maclaurin series to find the first 6 terms to an expansion of 1 plus x squared. So give you a normal fx function, 1 plus x squared, a set of 1 plus x. You're required to get the first 6 terms of the Maclaurin series. Yeah? So as usual, we need to find fx, f prime, f double prime, and so on. So that will be our first step. Fx, and then you substitute x as 0. Okay. F prime, differentiate, and then substitute as x as 0. And f double prime, you get the value of f double prime 0. You find f triple prime, and then find the value of f triple prime 0. And then power 4, find the value of x being 0, substitute into f differentiated 4 times, yeah. And then move on to 5, because you need 6 terms here, right? Yeah. Okay, so you already have 6 coefficients, 1, 2, 3, 4, 5, 6. So it's sufficient. Yeah. So next, what you need to do, you need to look up for the basic formula that I showed you just now. Your Maclaurin series can be written in such a way. So you have got all the respective f0, f prime 0, double prime 0, triple prime, power 4, power 5, and so on. So you need only 6 terms, right? So what you do now, you just substitute accordingly. So this is how it will look like. So fx is 1 plus x power half equals to, when you put in f0, your calculation, it's 1 over 0 factorial. Okay, and then 1 over 0 factorial is 1, and then here you'll get half, or 1 factorial. 1 factorial is 1, yeah, so 1 over 2x, and then f double prime here, you will actually, whatever value you got of f double prime from the previous slide, you substitute in. Don't forget to factor in the 2 factorial. Okay, and then if it's negative, you put in negative here. Okay, and then triple prime, we got the values, substitute respectively all the values you got, and then factor in the factorials. 4 factorial, 3 factorial, I believe you know how to calculate, right? Okay, put it in the values and then simplify to a proper fraction. Right, and then don't forget your continuity plus dot dot dot. It has to be there as a series. Yeah. Next, we will look at the third learning outcome, which is to calculate the Maclaurin series for simple composite functions, or to come up with Maclaurin series for simple composite functions. So now we're going to look at how to actually write the Maclaurin expansion for composite functions. So in this case, we know that for all values of k, before this we looked at it as e power x. If it's e power k is similar, we just change the k to x. Okay, so this was the general formula for expansion of e power x. Okay, so if the x changes to another value, we just need to substitute the k with the new x values. So for example, if you wish to expand e to the power of ax, it will be the same pattern. Instead of k, it will be ax, right? So we just need to substitute k with ax. It will be simply substituting k with ax, and you will arrive to this, another set of power series. If you wish to find a power series of an expansion which is ax plus b, you need to set k as ax plus b. Say you set k as ax plus b, then you will get this expansion. Right? Now, this is not a power series anymore. Right? This is not a power series in terms of x simply because it has b, and we need to find a way to factorize it so that the, the ax plus ax stays as ax alone. So in order to do that, what we need to do here is, um, by looking at this slide, you should rewrite e to the power of ax plus b using index law. You can write it as e to the power of ax multiply e to the power of b. So by doing that simply, you can actually get EAX, which we already got in the previous slide, multiplied by EB. So each term, you just multiply by e to the power of b. Now this, because AX is to the power of n, each term, so therefore this is again can be written as a power series and can be written as a summation of power series. So what we can do here is, we can take the a power n out as a constant, and then e power b exists in each term, so therefore it's another constant, right? And we can write x to the power of n over n factorial, where this is a form of a Maclaurin expansion. Next, another example. If you need to express sine 3x plus pi over 3 as a power series in x, or in terms of x, yeah? So your first step would be, because it's an addition trigonometric function. So your first step would be, you need to actually expand it out. Okay, because we need to get rid of some constants here. So for example, sine A plus B, it is sine A cos B plus cos A sine B. Okay, this was the addition formula we learned in semester 1. A sine A plus B, so sine 3x plus cos B cos pi over 3. Okay, plus cos A cos 3x plus sine B sine pi over 3. Right? When you do this, you will realize cos pi over 3 and sine pi over 3 are actually constants. Right? That's what I meant just now. You need to identify some constants. So here, cos 60 is half and sine 60 is set 3 over 2. You substitute that, and then for the next step, you actually find power series of each of it. So in this case, we already know we can identify sin x, which we did in our previous slides. Yeah. So sin x, this is the power series. You need to refer the few slides earlier. Okay. So if sin x is such, so sin 3x will simply be substituting x with 3x, right? So it will become sine 3x plus 3 here, because we just need to substitute x with 3x. So it will become half sine 3x plus 3 here will be half plus sine 3x, right? So it's half sine 3x. So instead of x, it is sine 3x now. So wherever there is x, it will be substituted with 3x. So here you see x became 3x, x cubed became 3x cubed, x5 became 3x5, x7 became 3x7. Right? There's a continuity, so there's a dot dot. And then the second part is sec 3 over 2 is sec 3 over 2 multiplied by cos 3x. Okay. You need to work out the cos 3x basic power series yourself. Just follow the previous examples. Okay. So instead of sine is cos. So cos x now is cos 3x. So substitute x with 3x. So it is sec 3 over 2 multiplied by 1 minus 1 over 2. X square is here becomes cos x, sorry, the x square here becomes 3x square. X power 4 becomes 3x power 4, x power 6 is 3x power 6. Right? And then your next task here would be expanding and bringing the alike terms together. So you need to expand it and then bring the alike terms together. Yeah. So what is meant by alike terms are the same powers together as far as possible. Over here, you can see, you can factorize the half out, right? So I copied back from the previous slide. And then what I did was I expanded each individual term individually. I expanded, right? And as you can see, you can see a pattern here. There are x with the even numbers, then there are x with the odd numbers, right? There is x, there's x squared, so 1, there's x power 0 here, right? This is a number constant. Then there's x power 0, x power 2, x power 1, x power 2, x power 3, x power 4, x power 5, so 6, 7, and so on. So arrange it in ascending order so it's easier for you to see the pattern. Next, you can summarize both of these into this function. All right. Don't worry, in exams you don't require you to simplify. You can leave your answer in this line. All right. This is just to give you some thinking skills. Yeah. So if you need to compress it, the function, you need to collect the odd powers and even powers together. Okay. So in this case, you write 2n plus 1 as being even, x power 2n even, and 2n plus 1, x power 2n plus 1 being the odd ones. Yeah. So you can summarize it this way, right? Please try to work out. So what you need to do, you collect the even powers together of x and odd powers together, and then you can come up with this particular summary. Okay, and further from that, you can actually summarize the whole sum together. You can bring out, you see there's half in both, so you can take out the half out as a constant, and then factorize the alike term out, and then you will actually summarize to this summation of the power series. Next, show you some simple, here I will show you some simple example of power series that we use very often for Maclaurin expansion. So example, e to the power of x, this is what we did in detail in the one of the previous slide. Yeah. Okay, so when you do the entire process of Maclaurin expansion, you arrive to this answer. If it's ln 1 plus x, please try it out. You will arrive to this answer. And sin x, we worked it out just now, one of the slide. Cosine x, I'm sure you have tried it based on the previous example. Okay, and an inverse tangent, you'll get this. So what you need to do is you need to sit down and work out each of it, and then substitute it into the Maclaurin expansion formula. And if it's 1 plus x power n, you will actually arrive to this. If you realize we did it just now,